In this video, I'd like to introduce a tool we can use to get inverses of analytic function that we already know. So let's jump right to it. Okay, so we already know that the log function is analytic, but let's start here. So recall that as long as we have non-zero z, we can define our capital L log as natural log of the modulus of z plus I times the argument function of z. And here I'm using the capital A arg, which means it's the principal branch of the argument function. So argument function gives you an angle that the complex number z makes with the positive real axis. And the capital A one guarantees you an angle between negative pi and positive pi, including the positive pi. Okay, if I mean to write the multi-valued version of the log, I'll use the lowercase l and the lowercase a for the argument part of the function. And basically what that means is that we'll get lots of different inverses of z's, each of them that are 2 pi I apart. So there's infinitely many solutions there. Okay, so let's just compute a few things to get used to this function. Log of 1 is natural log of absolute value of 1, which is 0. And argument that the positive number 1 makes with the positive real axis is 0. So log of 1 is still 0 in the complex sense. We can start to take logs of imaginary numbers. So let's try taking it. So log of I, so the modulus of I is 1. So the real part is still 0. But now the argument of I, so I makes 90 degrees or pi over 2 radians with the positive real axis. So pi over 2I is going to be the log of I. We could even do log of negative 1. So the argument of negative 1 is positive pi. Okay, and we could do other complex numbers as well. So 1 plus I, if you kind of sketch that, maybe it's easy to see that this is a 45-degree angle or pi over 4 radians. So that's what the argument makes. And the modulus of 1 plus I is going to be square root of 2. So natural log of square root of 2 plus pi over 4I. Hopefully this makes sense and we're getting used to how log function computes. Some notes about log function. So log is made up of lots of different pieces. So I think it helps to look at it one at a time. So looking at the modulus of a complex number is continuous on the complex plane. Right? As you change z a little bit, the modulus only changes a little bit at a time. So the natural log of modulus of z is continuous as long as we stay away from 0. So natural log function blows up at 0. So we want to avoid that to be continuous. The argument function is continuous as long as we stay away from the negative real axis, because remember, that's when the angle jumps from positive pi to negative pi, right? So we have to have a slit domain for it to be continuous. So if you make up a function with all these parts, right, the capital L log of z is continuous as long as we stay away from the negative real axis. Okay, And here's a trick we could use to compute the derivative of the log function. So we know that log function is an inverse to the complex exponential function. So we know that e of log of z is equal to just z. From here, if we take the derivative of both sides, we could use the chain rule on the left, and derivative of z is just 1 on the right. So derivative of e to the log of z is e to the log of z. And by chain rule, derivative of the log. So let's pretend we don't know what this is. And the right-hand side is equal to 1. Well, even if we don't know what the derivative is here, we could just solve for it. Bring this over to the right-hand side by dividing. And now I could just rewrite e to the log of z is just z. So the derivative of log is 1 over z. This trick could be used to get the derivative of the inverse for any analytic function. So here's a tool, theorem. Suppose that we have an analytic function, and we also know that the inverse is continuous in such a way that f of g of z is equal to z, right? So that's kind of like this situation where f is the e function and g is the log function here. Okay. We could take the derivative, use the chain rule, and then solve for the derivative of the inverse. And the derivative of the inverse function is going to be 1 over derivative of the original function evaluated at the inverse of z. Okay, so this part is a little bit weird because well, derivative of e was e, so maybe it wasn't as clear what the formula would be, but this is the general formula we could use for other inverses. Okay, let's try using it. So we could show that the square root function is analytic, and we can get the derivative at the same time using this theorem. So let's use it. So let's say that the original function is z squared, and we know polynomial is analytic, so we're good. And we know the derivative, it's equal to 2z. And let's look at the inverse here. So we want to look at the square root of z. Note that square root of z has 2 branches, right? We take the modulus, square root of the modulus, and you can take plus or minus the argument divided by 2, right? Remember, any nth roots have n different solutions. So square root has 2 solutions. So let's say the principal branch. So I'm going to use the capital arg function divided by 2. Okay, so this is one of the branch of the square root of z function. I hope that makes sense. And then let's see what the derivative would be. So using the theorem, the derivative is going to be f prime. So f prime is 2z. And then we plug in the inverse into the z in the derivative. So f prime is 2z. And then if you plug in g of z in there, g of z is the square root of z. So that's what goes in there. And here, I'm using the principal branch, or at least in my head, that's what I'm thinking of using. Okay. I keep using the principal branch, but we actually don't have to always restrict ourselves to the principal branch. So if you wanted to use a different branch of argument, you just have to specify a branch of argument. So remember, argument is going to give an angle. So you just have to give an interval 2 pi length, right? So with the principal argument function, we're going to go from negative pi to positive pi. That's what we did. But, you could use argument from 0 to 2 pi. So that still covers 2 pi radians. And this will give you a different branch. I hope that makes sense. Okay, let's do inverse sine function. So I promise you this computation is going to be bonkers. You'll love it. Okay, so we want to find inverse. So let's say z is given, and we want a w so that when we plug it into the sine function, we're going to get z. So remember, this is the complex definition of the sine function. Okay, so what I'm going to do here is simplify a little bit. We're going to substitute u is equal to e to the iw. So this part is equal to u, and e to the negative iw we could just rewrite as 1 over u because of the negative exponent. If you bring 2I to the left-hand side, we get this. We can multiply both sides of the equation by u and bring everything to the right-hand side. So we get u squared, and 2izu, we're going to bring to the right-hand side and make it negative 2izu. And if I multiply 1 over u by u, I just get negative 1 here. Okay, so what does this get us? Well, we get a quadratic equation in terms of u. So thinking of z as a constant, it's a given number to us. We could use a quadratic formula. So if we plug that in, we get this, right? Negative b plus or minus square root of b squared, which is that, minus 4 times a times c, so that's plus 4, all over 2 times 1. Okay, this simplifies a little bit. This 2 and the 2 below cancels out, and factor of 4 could be factored out, and then square root of 4 is 2, so that 2 also cancels with the 2 on the bottom. So yeah, if we simplify, this is what we get. Or there's 2 branches of the square roots, right? So I could write plus or minus here, but really I'm just thinking of like 2 branches of the square root function, and that's going to be the u. Okay, u is almost what we want, but what we really want is w. So to go from u to w, we have to take the natural log to get the inverse of e, and then divide by I. Okay, so the arcsine function of z in a complex sense is going to be 1 over I is same thing as negative I. So I'm going to write it as negative I times log of u, which is this bit. Now, this is a multi-valued function. There's actually lots of answers to the arcsine. And that's kind of expected because sine is a periodic function, right? Like every time you add 2 pi to your input, you get exactly the same thing. So we do expect this to be multi-valued. But this actually, it's a little bit more complicated than that. It's multi-valued in a couple sense. There's 2 branches of the square root function. So when you do the 1 minus z squared and square root that, you get 2 choices. And then for the log function, the imaginary part of the log function is the argument function. So there's an answer for every 2 pi I. You'll get another solution as well. So that's a lot. So let's do an example computation just to kind of get a hang of this, how to get the multi values for this arcsine function. Okay, so what we're going to do is we're going to compute arcsine of 2. So if you type this into the calculator, it'll say domain error, because usually the inverse sine function has to be between -1 and +1. But that's the usual arcsine function in the real sense. If we're looking at the complex arcsine function, you could actually achieve 2. So let's see what happens. So we're going to plug it in. So -I times log of, we have iz here, so 2I plus 1 minus 2 squared. So 1 minus 2 squared is going to be -3. And we're going to take the square root of that. Okay, so the negative square root, we're going to get I. So square root of 3I and plus or minus, because we have 2 branches, so we have to keep track of both. Inside of the log is purely imaginary, right? So you could factor out the I here. We get 2 plus or minus square root of 3 times I. Okay, so let's use the complex definition of the log function here. Okay, so we're going to take the natural log of the modulus of this guy plus I times the argument of 2 plus or minus square root of 3 times I. Okay, let's do the argument part first. Okay, so 2 plus or minus square root of 3, like it's going to be positive, right? So 2 is larger than square root of 3. So even if you subtracted square root of 3, you're going to have a positive number. So, okay, here's so 1, 2. 2 minus square root of 3 is something like that. Times I. Then there's also another value over here. 2 plus square root of 3 I. Either way, it's purely imaginary. So argument is going to be the 90 degrees, pi over 2 radians. So this argument is pi over 2 plus any multiple 2 pi shifted, right? So I'm going to add plus 2 pi k for any integer k. And I should have an I in front here, but I'm also distributing a negative I to both of these terms. So I times negative I is just positive 1. So this is the argument part. Okay. Now I have to compute the natural log part. Well, what's the modulus of 2 plus or minus square root of 3? It's just 2 plus or minus square root of 3. So we have two answers there. So there's 2 possible imaginary values. Then there's infinitely many like 2 pi apart real values that works. So what did we just compute? If we plug this into the complex sine function, we're going to get the output of 2. That's crazy, right? Okay. So I've done the work for arcsine function, but of course you could do similar stuff to get the inverse cosine function, which looks very similar. This is the formula for arc cosine. Yeah, they're very similar. You just change the location of I inside of the log. That's the only difference. And then if you do the analysis for arctan function, that's what you get. I over 2 times log I plus z over I minus z. I love the arctan function. Okay, I hope you enjoyed that computation. This is where I'm going to end the video.